In wave optics, we shall deal with simplified scalar wave theory, and we shall discuss phase and group velocities of light waves, phenomena of interference and diffraction of light. This topic shall be divided into 11 lectures. We shall start with introduction of wave equations as well as electromagnetic waves and Doppler effect in lecture 8. This is followed by superposition of electromagnetic waves and creation of standing waves in lecture 9. In lecture 10, we shall continue on bits phenomena as well as phase and group velocities. In lecture 11, we shall discuss the concept of coherence in dealing with light interference as a precursor to lectures 12 and 14, where light interference in a few interferometer arrangements shall be explained. Wave optics shall conclude with Fraunhofer or far-field diffraction in lectures 15 to 17. And we shall start with lecture 8. Wave theory of light encompasses the ray theory, as you can see over here, and ray optics is the limit of wave optics when the wavelength of the light is much smaller than the dimension of the object. Over here we compare the size of the object with the wavelength of the illumination. Ray optics is used when lambda is much smaller than d. When lambda is larger than the dimension of the object or the aperture, then wave optics will be applicable. And it can describe light using scalar wave function. So we will be using the scalar wave model. However, wave optics cannot sufficiently describe the reflection and refraction of light at boundaries between dielectric media, for example, Fresnel's equations, and it cannot sufficiently describe optical phenomena that require vector formulation, especially in polarization of light. However, wave optics can describe interference and diffraction. Let's look into wave equations. This diagram shows one-dimensional wave equation. So we consider a wave pulse of arbitrary shape here, but it is time independent given by a function y prime equals to a function of x prime here. The coordinate system with the origin O prime here will move to the right at a uniform speed of v relative to the fixed coordinate system O. The pulse shape, as you can see here, it is maintained while it moves. If you take a point P, it can be described either by x or x prime, where x prime will be equals to x minus the distance moved within time t, and that is vt. From the reference of a stationary coordinate system, moving the pulse then is expressed as y can be equated to y prime, and that's equals to the function of x prime. Then substituting x prime, it can also be expressed as a function of x minus vt. Hence, the general form of a traveling wave would be a disturbance y here as a function of x, which is the direction that it is moving, plus or minus the speed of that traveling wave multiplied by t. The speed is positive when the wave is moving to the left, and it will be negative when the wave is moving to the right. And f here stands for any function. The partial differential equation that represents wave equation and it is satisfied by all traveling waves can be derived in this way. We start from y equals to a function of x prime, where x prime here can be expressed as x plus or minus vt, from which if you take the partial differential of x prime to x, that's equals to 1. And taking the partial differential of x prime to t, that will give us plus or minus v. And using the chain rule, the space derivative is then given by del y del x, and that's equals to del f del x prime del x prime del x, and that can be written as del f del x prime. And its second derivative given by del squared y del x squared will be taking the derivative respect to x of del y del x, and then changing this del x to del x prime, we will multiply by del x prime over del x, and that gives us taking the derivative with respect to del x, substituting this one here with this one here, we have del f del x prime, and this derivative here is equals to 1. So we can then write this one as del squared f del x prime squared. Similarly, we can do that for the time derivative and its second derivative as well. So that will give us del y del t equal to del f del x prime multiplied by del x prime del t, and that's equals to, whereby here is substitute with plus or minus v del f del x prime. And taking the second derivative, it will be equated to taking the time derivative of del y del t, substituting over here del x prime, then we multiply by del x prime del t, and that will give us whereby del x prime del t here is substituted with plus or minus v, and del y del t is given by plus or minus v del f del x prime, and from this we will get v squared del squared f del x prime squared. Combining these two derivatives here will give us the one-dimensional differential wave equation. We can relate the second derivative respect to space to the second derivative respect to time. That is, this equation relate to this equation, and here we have this term as common. So del squared y del x squared will be equal to 1 over v squared del squared y del t squared. So any wave that is of the form given by this tells us that it's a traveling wave, and it must satisfy this wave equation irrespective of the physical nature of the wave itself. Harmonic waves can be expressed using cosine or sine function, as can be seen in these two expressions here. Y equals to a sine k into x plus or minus vt, or y equals to a cos k into x plus or minus vt. For phase that is constant, so the change of this phase will be equal to 0, which means that k into dx plus or minus v dt will be equal to 0, and that will give us dx dt is equal to negative or positive v. And when we say constant phase, it actually describes the motion of a fixed point on the waveform that moves with the velocity of the wave v. If the phase is expressed as k into x plus vt as time increases, then to keep this term constant, x will have to get more and more negative. In other words, the wave is traveling in the negative x direction. Whereas when a phase is written as k into x minus vt, as time increases, this term here will get more and more negative. So x will have to get more and more positive, meaning the wave will be traveling in the positive x direction. And if there exists an initial displacement of phase of a phi 0, then we insert that into the phase term like this. The phase can be expressed differently, as is shown here, where k has been replaced by 2 pi over lambda, and for the time term, kv has been replaced by 2 pi over t, where uppercase t here is the period of the wave. Or The phase can be written as kx plus or minus omega t, where this is the angular velocity. And this table gives the usual symbols used for representing the wave. In complex notation, the harmonic waves can be written as a exponential I into kx plus or minus omega t, whereby the real part of this expression will be a cos kx plus or minus omega t, and the imaginary part is given by a sin kx plus or minus omega t. Which is obtained from Euler's formula given this way, whereby this is the real part and this is the imaginary part. This table lists the frequently used values of exponential I theta, whereby theta takes value of 0, pi over 2, pi, or 3 pi over 2, and the exponential function will give these values. Next, we look at plane waves. What is a plane wave? It is a wave whose surfaces of constant phase, which are represented as these planes here, are infinite parallel planes normal to the direction of propagation. We can generalize the wave equation, whereby the wave displacement now is represented by a scalar function. Instead of the y that we use, we have a psi here, and that's equal to a sine into kx minus omega t. Since this is negative, the wave is traveling in the positive x direction. The psi here can represent any quantity that varies in space and time. This figure here shows a plane wave that is traveling in z direction, and it is a periodic function of z with spatial period of lambda, and it is also a periodic function of time with a temporal period, which is from here to here, which is reciprocal of the frequency. For a monochromatic wave that propagates through a medium of different refractive indices, its frequency remains the same, but the velocity, the wavelength, and the wave number will change. The speed can be given as C0 over n, where n is the refractive index, C0 is the speed of light in vacuum, and lambda will be given by lambda 0 over n, where lambda 0 is the wavelength in free space, and k, which is the propagation constant, and that's equals to n multiplied by k0. K0 is the propagation constant in free space. The plane wave at a fixed time, say t equals to 0, will be expressed as psi equals to a sine kx. At fixed x, the phase kx will be a constant. Surfaces of constant phase make up the family of planes perpendicular to the x-axis, that is, these planes are the wavefronts of the disturbance, as shown in this diagram. The plane wavefronts at x equals to a, x equals to b, and x equals to c will be perpendicular to the direction of propagation of the wave. The wave displacement psi at all points on the same wavefront will be the same. Here we would like to consider a plane wave that travels in an arbitrary direction k. The harmonic wave is given by psi equals to a sine kx minus omega t. We shall take an arbitrary point in space, as shown in this diagram here, where the propagation vector k is in the x direction, and we shall take time equals to 0. The wave disturbance then at this arbitrary point, defined by position vector r, is the same for point X along x-axis, whereby X is given by R cosine theta. Hence, the wave disturbance becomes psi equals to A sine kx. And substituting for x here, it will be given as A sine of kr cos theta. Now, what if the propagation vector k is in an arbitrary direction as shown here? It makes an angle theta with the position vector r, such that the dot product will be given as kr cos theta. Then the wave disturbance of this plane wave will be written in a general form as psi equals to A sine k vector dot with r vector minus omega t. The general form of the harmonic wave in 3 dimensions can be written in complex form as psi equals to A exponential I into k dot with r vector minus omega t. And this will satisfy the 3D partial differential equation given in a generalized form, taking the second partial derivative respect to the space coordinates of x, y, and z. That will be equal to 1 over v squared multiplied by the second derivative of the wave function respect to time. And this term here can be expressed by the Laplacian operator. So here we relate the second derivative with respect to space to the second derivative of the wave disturbance with respect to time, and they are related through a factor 1 over v squared. Let's look at the spherical waves emitted from a point source in a homogeneous medium. They travel in all directions at equal rates. Their wavefronts form spherical surfaces centered at the point source, and the harmonic spherical wave is expressed as psi equals to A over R multiplied by exponential I into kr minus omega t, whereby r is the distance from the source, k is the angular wave number, a is a constant. This will give the amplitude of the wave. This expression is a solution to the differential wave equation given by this expression. Looking at the spherical waves, the amplitude decreases as it propagates further from the source, or you can see over here, the wave decreases in amplitude as it moves further from the source. And the constant A here corresponds to when the wave is at a radial distance equals to 1 from the point source. And the intensity of this wave is proportional to the square of this expression here. Next, cylindrical wave disturbance can be expressed as psi equals to A over root rho multiplied by exponential I k rho plus or minus omega t. Rho here is the perpendicular distance from the line of symmetry to the point on the waveform. And rho is given as the square root of x squared plus y squared. The wavefront is cylindrical in shape. Do note that the wave of this form is not an exact solution to the differential wave equation, and so it will not represent the physical wave, but it is approximately valid when rho is large, but it is still a useful form that approximates the wave that emerges from a slit illuminated by plane waves. Light propagates in the form of waves, and it is an electromagnetic wave. In free space, it travels at speed equals to 3 times 10 to the power 8 meters per second. For the infrared region, which is here, its wavelength is from 0.76 to 300 microns. That corresponds to 1 to 400 terahertz, where tera means 10 to the power 12. And the visible range is short here. It would range from 390 to 760 nanometer, equivalent to 400 to 800 terahertz. And the ultraviolet range is from 10 to 390 nanometers, and that's equivalent to 0.8 to 30 petahertz. Peta is 10 to the power 15. So light has electric field and magnetic field. Consider a plane electromagnetic wave. So we have the electric field vector and the magnetic field vector, and it propagates in this direction. And all these three vectors are mutually perpendicular. The E and the B fields can be described by harmonic equations as E equals to E0 sine of K dot R minus omega T, and B equals to B0 sine of K dot R product minus omega T. Both the E and the B wave will travel with the same angular wave number and frequency omega, and thus with the same wavelength and speed. Wave fronts for a linearly polarized EM wave are planes that are perpendicular to the direction of propagation. The E and B fields' amplitudes are related by a factor c, which is the speed of light. And at any specified time and space, E will be equal to Cb, and the velocity c in free space is given by a reciprocal of the root of epsilon 0 and mu 0, whereby epsilon 0 is the permittivity of free space, mu 0 is the permeability of free space. The electromagnetic wave represents the transmission of energy, and the energy density associated with the E field in free space is given by half epsilon 0 E amplitude squared. And the energy density associated with the B field in free space is given by 1 over 2 mu 0 B squared. And the unit is joules per meter cube. The two energy densities are equal from this relation. Substituting B with E over C, squaring it, and substituting 1 over C with epsilon 0 and mu 0, we will then get half epsilon 0 E squared, which is equal to the energy density associated with the E field. In other words, the energy of the EM wave is divided equally between its constituent electric and magnetic fields. Therefore, the total energy density would be the sum of the two of them. So you can write it as 2UE or 2UB. Now, the power is defined as the rate at which energy is transported by the EM wave, and its expression can be obtained by considering a time interval delta t, where the energy flow of the wave associated with a volume delta V, that's shown here, of cross-sectional area A multiplied by the distance that the energy flow of the EM wave has made, that's equal to C multiplied by delta T. Hence, the power will be given as energy over the time interval, and energy is written as energy density multiplied by the volume, and substituting the volume with the area and the distance traversed, that will give us UCA. rewriting the energy density as splitting the U into a root U multiplied by a root U, and each of this is substituted with the value that's associated with its E field and the B field, and that will give us epsilon 0 over root of epsilon 0 mu 0 EB, whereby 1 over root of epsilon 0 mu 0 is substituted with C. So in other words, the energy density can then be written as epsilon 0 C EB. The power transferred per unit area is given by the energy density multiplied by the speed, and that's equals to epsilon 0 C squared EB. And in vector notation, this power transferred per unit area is called the Poynting vector, where it is equal to the cross product of the E and the B field multiplied by this factor here. And E and B fields are orthogonal fields. The magnitude of the Poynting vector varies rapidly in the range of 10 to the 14 to 10 to the 15 Hertz for visible light. Hence, it's more appropriate to take the average value of one full wave, that is the irradiance value, which is defined as the time average of power delivered per unit area. And so we will take the time average given by this bracket here of the E cross B field, where E is represented by E0 sine k r plus minus omega t, and B field is given by B0 sine k r plus or minus omega t. So this expression here has a sine squared term, and the average of sine squared term functions over one period will give you a value of half. In that case, the irradiance then would be written as half epsilon 0 C squared E0 B0, where E0 and B0 are the amplitude for the respective E and B fields. This is the invariant form. In the case of a medium of refractive index n, then we will have to replace the permittivity by n squared epsilon 0. And the speed here will be replaced by V, which is equals to C over N. Here are other properties that we can define for light waves. The optical intensity or irradiance, which we have already defined earlier, which is the optical power per unit area, that will be proportional to the average over time of the square of the wave functions. And the optical power, or what we call radiant flux, flowing into an area A that is normal to the direction of propagation of light, will be given as the integral of the irradiance over the cross-sectional area. The optical energy, which we call the radiant energy, collected within a given time interval, would be the integral of the optical power over the time interval specified. Here is a sample question. If you have a laser beam of radius 1 mm and it carries radiant power of 6 kilowatt, what would be the average irradiance and amplitude of its E and B fields? The average irradiance is given by the power per unit area, and that would be 6,000 divided by the area of the laser beam, which is pi r squared. And that will give you 1.91 times 10 to the power 9 watts per meter squared. Making use of the irradiance, the amplitude of E field will be given by root of 2 multiplied by the irradiance divided by epsilon 0 C. And this will give us a value of 1.2 times 10 to the power 6 volts per meter. And the amplitude of B, which is related to E through a factor C, then this will give us 4 millitesla. Now let's look at Doppler effect. For sound waves, which are longitudinal pressure waves propagating through a medium, the resulting frequency shift that depends on whether the source is moving towards or away from the observer is based on change in transmitted wavelength. If the observer is moving instead of the source, the frequency shift will be based physically on the change in speed of sound waves relative to the observer. Both these effects are distinct, being described by different equations. In the case of light waves, which are transverse EM waves assumed to propagate in vacuum here, there is no medium of propagation, hence no physical basis for distinguishing between moving observer or moving source. Here we define only one relative motion between the source and the observer that will determine the frequency shift. To derive the Doppler effect for light waves, the theory of special relativity is required. However, we will not discuss that here. If lambda prime is the Doppler shifted wavelength and v is the relative velocity between the source and the observer, then the Doppler shifted wavelength lambda prime will be given by the root of 1 minus v divided by c divided by 1 plus v divided by c multiplied by the original wavelength. V would be positive when the source and the observer are approaching each other, and it will be negative when they are separating from each other. For relative velocity, which is much smaller than the speed of light in vacuum, this expression then can be approximated by we multiply the numerator and the denominator by 1 minus v over c, and this will give us 1 minus v over c squared. Here we will get 1 minus v squared over c squared. And when v is much smaller than c, this term is close to 0. And that will give us just 1 minus vc. And hence the ratio of lambda prime to lambda can be approximated to 1 minus v over c. This Doppler effect is used to find the speed of astronomical sources that emit electromagnetic radiation. When the astronomical sources, for example, the stars, are moving away from us, then we will see a rate shift in the wavelength of the radiation detected. In other words, this detected wavelength will occur at a larger value. Here is an example that characterizes this shift in the wavelength from astronomical source. Light from a distant galaxy shows the characteristic lines of oxygen spectrum, of which the standard spectrum can be measured in a standard lamp source in the laboratory, except that the wavelengths that was collected from this distant galaxy seem to be shifted. The line that was expected at 513 nanometer now shows up at 525 nanometer, so there's a shift to longer wavelength. What is the speed of the galaxy relative to Earth then? So the shifted wavelength lambda prime is 525. Substituting these values into the equation in the previous slide, that will give us 525 divided by 513 equals to 1 minus v over c, where c is the speed of light in vacuum. So from this, we will find that v is negative 0.0234 c, and that is equal to negative 7,020 kilometers per second. And since it's negative, then this galaxy is moving away from Earth. So as this shifted wavelength is longer, the galaxy is therefore moving away from Earth with a speed of about 7,020 kilometers per second. Here are the learning outcomes for this lecture. After going through this lecture, you should be able to define and distinguish the differential wave equation, and you should be able to write harmonic wave functions in complex form. You should be able to distinguish between plane, spherical, and cylindrical waves, and you are able to describe the properties of EM wave as well as derive the irradiance of EM wave. And finally, you should be able to describe Doppler effect for light wave. Thank you for listening.